Okay, let's get started. I'd like to thank everyone for joining us today. Welcome to today's CNCF webinar, Making Data Work for Developers with Kubernetes and Cassandra. I'm Jerry Fallon, and I'll be moderating today's webinar. I would like to welcome today's presenters, Chris Splinter, Senior Product Manager of Developer Solutions at DataStax, and Patrick McFadden, VP of Developer Relations at DataStax. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There's a Q&A box at the bottom of your screen. Please feel free to drop your questions in there, and we'll get to as many as we can at the end. This is an official webinar of the CNCF, and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinar page at cncf.io/webinars. With that, I'll hand it over to Chris and Patrick to kick off today's presentation.
Great, thanks a lot, Jerry. Well, this is gonna be a fun-filled, I don't know how long this is gonna take. Probably less than an hour because that's all we're given. But we're gonna talk about Cassandra and Kubernetes. It's a really hot topic. I seem to be talking about this a lot. I mean, same with you, I'm sure, Chris. You gonna say yes? Okay, yeah.
That's fun. Yes, absolutely. We're excited to talk about this today.
Yeah, so we've been working on a few things together. Kubernetes Operator for Cassandra is one thing, working inside the Apache Cassandra community as well as CNCF. So with all these things coming together, we thought we would give you a good picture of why developers and operators are moving towards this paradigm, but also to give us all some sort of a some indications on like where this is going. We have some case studies in there, so let's do this. So next slide. So we're gonna talk about this move right here, which is going from monoliths to microservices. And what's surprising to me is just how much monolith really still is out there. And this is a huge thing around digital transformation, as you see like right now, especially in as everything is moving towards online. Monolith, you know, it's funny, Chris, I always think of monolith as like a mainframe. But
and in a lot of cases it is, but in also a lot of cases it is not. Like we're seeing Istio go back actually from microservices to monolith, which is certainly interesting.
It is really cool. I've seen SOA and microservices run on a mainframe. There's CICS, there's WebSphere on CICS that runs microservices now. So go IBM. So this is what we actually want you to think more about in a microservice architecture is being distributed. Distributed computing is a very important paradigm in how we deploy applications because it gives us the ability for the scale, for the resilience, for the elasticity that's really important for today's applications. So when we go from monolith, you know, we usually, I think this is where we see most are either in this multi-tier SOA world right now. I think, you know, you break up your front end, your back end, and your data layer. Classic, you know, this is the old school LAMP actually was more the multi-tier. The service-oriented architecture is still pretty valid, but that involved things like enterprise, what am I trying to say here? Java beans. Remember back in the day when we had those, and the buses, the service bus, and how things were talking. It was basically the multi-tier broken up into these really nice constituencies. And now with microservices, it's interesting. This is not new. I remember Netflix talking about this in 2011, 2012, is how they built Netflix. It was all these distributed microservices. And each service was really this an individual part of Netflix, probably run by a team, a small team, but it created that resilience that they really need. And so let's move on to the next thing. So when we're building microservices, there's a few things you need to think about. I've highlighted, there's a lot of things actually, and this is from the Microservices Patterns book, but I've highlighted three things here. First is the observability. You cannot distribute that much infrastructure without knowing what's going on, unless you love surprises. Some people love surprises. Chris, do you love surprises?
No.
Not in my infrastructure. No. And, you know, I used to run infrastructure. Those surprises always came at what, 3 a.m., 2 a.m.? Why doesn't anything break during the middle of the day? And testing, how to prevent, again, the least surprises. If I test something properly and I put it into production, awesome. Hopefully it won't surprise me, but I'm still gonna watch you, services. But then the other part is this, this database per service. And that probably creates a lot of havoc with the architect mind, because wait a minute, don't we centralize our database? Don't we build the big monolith database, the one database to rule them all? Not in this world, not in a distributed computing world. And I think this is what we need to dig in a bit on building microservices. And then you'll see like how this is a form fit for how Kubernetes works. So next slide, please. So that one database per service. And it seems like you got a lot of infrastructure here, but you do, but you don't. You're going to build a distributed system and it will scale as you need it. So as big as it gets is as big as you need. And I'll tell you, when you have a Cyber Monday event, you'll be really happy you did this, because that's when you need it. So what do you need? Everything needs to be loosely coupled. And loosely coupling services, that is, I think, an obvious thing for microservices people, but sometimes we lose track of that. Like I've seen people build microservices where they have a chain of dependencies, and if one microservice breaks way down the chain, everything goes down. That is not the right way to do it. The circuit breaker patterns, the way that they're coupled with APIs instead of a direct TCP/IP connection, that, you know, a stateful connection to a database is a bad idea. And so each service in that case is going to be isolated. So you service your data, they're isolated and they store the state for that service. So instead of having, again, like a database that's running every single service in your infrastructure and your application, which if it goes down, your entire app goes down. What if you lose one service? I'll give you a good example. I saw a talk from Hulu years ago that talked, they're a huge Cassandra shop, and they talked about how they manage outages. And it may be that if they lose a microservice or a database, something happens, they lose connectivity. It just, their way that they build their service was it just won't show you that feature. And you could still watch Golden Girls or whatever you love on Hulu, but I'm pretty sure that's the only thing on there anymore. But you could still watch TV shows, movies, things like that. You just may not have like one piece of functionality. Maybe the search isn't working very good. Yeah, that's just not very fun, but it doesn't ruin everything. So that's one part of it. And then how does that relate to Cassandra? Well, Cassandra is really built for failure, and not yours, the inevitable failure that will happen in infrastructure. I don't think anyone's ever deployed something in any size of infrastructure and expected it to be up 100%. So by spreading things around, we're doing a better job of keeping our uptime going. So when we share a database, you know, that's this coupling of data. Shared database is not equal shared data. So we're keeping that isolation, a key space, a table, and the access control is all these one-to-one relationships between the services and what you're deploying behind it. And I will explain how this works in Cassandra land. But when you're building up all this infrastructure, you're going to have a lot of different Cassandra clusters being deployed, say in Kubernetes. You're going to have the right replication factor, so that even if you lose small parts of it, it's still online, and you're eliminating the ugly, horrible thing of a single point of failure. And single points of failure, we try not to put them into our systems, but sometimes we're forced architecturally to do it. I'm saying don't. When you use Cassandra as a database, it doesn't have a single point of failure. And when you're using Kubernetes, it shouldn't have a single point of failure. But I think both, you can do bad things and rig up a single point of failure. If you're using a relational database with one server in it, that's a huge single point of failure. Next slide, please. And speaking of relational databases, How many times have I heard this? Well, I need ACID. This is atomicity, consistency, isolation, and durability. That has been a paradigm that has changed with NoSQL. NoSQL, it really was about non-relational databases. And it's because ACID compliant databases were built in a time when we had one database and there were tens or hundreds of users. And the consistency was important because we really had a hard time maintaining any consistency anyway. So this is where we got the thing around two-phase commits. And the transactions that happened had to be a two-phase commit or it never happened. Funny thing is that a lot of databases, the largest databases in the world at the time were not ACID compliant, like mainframes. They did ledger reconciliation inside of the database to make sure that things got merged properly. We learned a lot about that. If you look at the original Cassandra paper, which goes back to the Dynamo paper, these are computer science papers, there was a lot of references to stuff that was learned in the mainframe world in the 1970s about how to keep data consistent in this loosely coupled world. This is where we live. So what we're talking about as a change, just because we want to talk about chemistry, instead of acid, how about some base? And that's that basic availability for saw state and eventual consistency. Eventual consistency probably strikes the most fear in people's hearts. They're like, wait a minute, if I commit data into my database, what is it going to be like next week when I see it? You know, it's like, no, that's not what this is about. That means that if you do a write and you do a read at the same time, you may not get the exact same write unless you ask for it. That's where consistency comes in. So we can change the consistency. We can say, I want it to be that consistent, or I don't need it that consistency. You need to be able to have that flexibility. That basic availability is more important. If you think about like a database that stores a product catalog, and it's the middle of the holiday shopping season or Cyber Monday, the availability is going to win in that case. I need to have it. And I think that's where you see like where banking, most banks use Cassandra now because availability is more important than that strong consistency, believe it or not. It will be consistent, but having the availability, being able to check your balance and do transactions is more important 24/7 than doing an ACID transaction. Banks don't do that. And this event sourcing, saving the messages and not the final state, that is how that works. And so in cases where we don't have an absolute connection to the database where, yes, I have a complete picture of all data in the system, I want to be able to save that happened. Think of like, if I'm moving money from one place to another, I want a record that I said that. And if I check my balance and it's wrong, I don't want it to be wrong because that message got lost. I want it to be because there was some stale data in there, which is not always good either. But what's more important is the message got there and it can be rectified. And then finally, the idempotence. If I miss, if something happened and I, for whatever reason, redid it or something was out of order, I want to make sure that it's replayable and that it is idempotent. Idempotency is if I do the same thing over, it doesn't change anything. It doesn't update it to a new value. It just replays it exactly the same way. These are super important for today's applications. Mobile applications, retail applications, IoT, all rely on this. Next slide, please. So this is why when we're building things in microservices, Apache Cassandra just is like the database for this, and it's really the best database for Kubernetes in this case because of the way that it works. It manages things in real time, scales. It is the most scalable database around. It is running the biggest workloads on the internet right now. You don't know it, but you use microservices. You use Cassandra every single day, all day probably. It's in everything you touch. And it's just because it's one of those databases that works. And we're going from ACID to base. There's all sorts of things that are happening there. And Chris is going to go through some of the really cool use cases. But we're going to decouple by design. One key space per domain, one query per table. Simple. It's easy to architect, easy to deploy. Next slide, please.
All right, thanks, Patrick. Yeah, all of those considerations that you just talked about, they do certainly show, though, that the choice of going to microservices does bring a trade-off of complexity. And there's not necessarily a one-size-fits-all solution there, but what we've seen and what we'll cover in the next few slides here is that users are choosing Cassandra for their microservices when they need the same level of scalability and availability at the data tier that they have in their microservices that are running on Kubernetes. And we've been fortunate enough to be students of several architectural transformations over the past few years, and that's what we're going to cover here in the next few slides. So the first one is Monzo Bank, and I have to start by just saying thank you to the Monzo team for sharing their technical story in such depth so that people like us can learn from both their challenges and their successes. And I feel like a personal fan almost, because they've built some really amazing things over the years. And I recommend checking out their blogs and presentations because it really is a success story of microservices and cloud native. And so their use case is very much focused on banking and payments. And they've really had an eye on reinventing that industry from the start. So when they were just starting out, they really went for the microservices from the get-go. And I think their latest total is over 1,600 microservices, which is a pretty incredible number. And I remember their tweet with the connections between all of those microservices. And it certainly represents complexity. And they've done some amazing things from the tooling perspective to deal with all of that. But one of the main reasons that Matt Heath, who is a senior distributed systems engineer for Monzo, one of the reasons that he cites is the agility. And the example that he gives is with their Monzo card, they have functionality where a user can enable or disable it if they want to lock their card. And he said that that functionality took 10 minutes to build, which might be an exaggeration, but it's that sort of agility that people look to get to when they are considering microservices. And in Monzo's case, clearly it's been delivering for them. And then they chose Cassandra because of its scalability and availability attributes. And this is very important for specifically applications in the fintech space, because if any of us ever swiped our card and it didn't work, we would be in a significant amount of trouble. And right now they have over 500 services that use Cassandra, and the data isolation model that they went for is using a key space per service. So this is not necessarily the database per microservice that some purists may advocate for, but in their case, it's what works for them. And I could take a guess that this is because they have a team of platform engineers that are actually responsible for that database. So we start to see that microservices isn't just a technical architecture, but it also reflects the organizational structure. And at the end of the day, teams should do what makes sense from an organizational standpoint when planning and building their microservices. One of the other really important learnings from Monzo that I personally found so impressive is all of the tooling that they've built around their microservices architecture. There's no doubt that having one thing is less complex than having a lot of things. And some of the various pieces that they put together, I know one of their highest priorities is building their zero trust security network with special network isolation rules. And they also rotate Cassandra client credentials using Vault. Just really impressive work there from a security standpoint. And that game changes when they have so many of the different services that are deployed in Kubernetes. And one of the other pieces relating back to what Patrick was talking about with ACID versus base, they had a really interesting use case where they were doing crowdfunding, and they looked at using counters in Cassandra because they couldn't raise more than 20 million euro. That was their limit on their investments. So they ended up actually doing that kind of global tally outside of Cassandra because it didn't have those attributes. So I believe they used the Go Atomic package and then they flushed to etcd. But it shows that in these distributed environments, with distributed databases, there are solutions that don't necessarily go along the same lines as the same techniques that have been used in the past with relational databases. So again, my takeaways when looking at Monzo's use case, they really built for agility and scale from the start. This was both with their microservices architecture, but then also their choice of Cassandra. And then they've just been producing tooling to deal with the complexity of their microservices architecture. And it's really been impressive to see the things that are open and available on their GitHub. So that's Monzo. The next one here happens to be another banking and payment application. And this one is Mobile Pay, which is now a branch of Danske Bank. And this app started as something just to transfer money between friends. And since then, they've expanded to all sorts of different avenues of e-commerce, point of sale transactions, and partnering with banks. And just to throw out some of their stats, they've expanded to over 4 million users, 100 million Danish krone in transfers in 2019, and over 1 million transactions per day. And now it's an integral part of money transactions for Danes. And really the key learning from this example is how they went about their journey to microservices. And what started as just a simple native mobile app built upon their existing monolith, they actually had the chance to look at it and say, well, how would we build this thing? Because we know this is going to be an industry that witnesses a high amount of disruption. So they started with the business needs. And their 3 business needs were, well, this app has to be trustworthy. It has to be just as available as cash. The second one is they knew that they were going to need a lot of agility to innovate very quickly to keep up with competition. And the third was that they wanted open APIs to be able to expand their partnerships. So they started with those business needs and then mapped them to the technical principles and architecture, which ultimately ended up with what we're looking on this slide, which is bounded context for each service and different teams working on services in parallel. So again, the lesson there is starting with the business value, starting with the business needs. That's what should inform your journey and your path to microservices rather than just saying, we heard microservices are cool, we should do that. And they opted for a wide range of different technical options in order to execute on this design. And they have pub sub, so the event sourcing and event-driven architecture for resiliency and retry. They have separate security contexts around service heaps and an API gateway at the edge. Again, they're using bounded context and actually have polyglot persistence for active-active, which they use Cassandra for. And then lastly, their microservices are all exposed over well-defined REST APIs, which has allowed them to communicate cleanly across teams, but then also externally, such that they have a developer SDK for people to develop on their platform. So another really cool story where they started from the business value, ended up in microservices, and it's allowed them to greatly expand the capabilities of their mobile pay application. The next one, Intuit. This use case is TurboTax, which I'm sure we all know. We had a bit of an extension this year to pay our taxes in the United States, which was nice. But Intuit has a different model. In the previous Monzo model, they were doing key space per service, but Intuit actually has cluster per business unit. And again, this is where we start to see the organizational structure of companies reflecting into the technical architecture and them doing what makes sense for them as an organization. And so this is what they have is a persistent services team that runs all of their databases, and they're actually abstracting that to their development teams, which then build microservices through a REST API that they build on top of Cassandra. But there's several microservices that this persistent services team runs to power TurboTax. And they support over 300,000 concurrent users in production. Their largest cluster is 144 nodes across 2 regions. So again, we see that same distributed scalable type of a nature at the data tier as we do at the microservice tier itself. And the other interesting thing about Intuit is that they actually have a multi-tenant data store where they have over 500 schemas that are supported, and really the storage for that is transparent to the developers that are consuming them. But they've also built tooling so that developers can just check in their schema to GitHub. It goes through their schema pipeline and pushes into the database itself. So the story here is, again, organizational structure reflecting into what makes sense for the technical structure, choosing Cassandra for scale, availability, and performance. And then, again, they had to home grow a lot of tooling. And recently, they actually released an open source product called Pronto, which can be used to administer and automate Cassandra clusters on AWS. And then the last one I want to talk about here that, again, illustrates the key space per service data isolation model is Walgreens. They're the retail pharmacy, have many prescriptions filled daily, and have 88 million active balance rewards customers, and I am one of them. So they architected for active-active. That was very important to them. And then again, they go with the combination of key space and user per microservice. And in the same pattern, they also built a lot of custom tooling in order to push through their different schemas and DDL code through their DevOps pipeline. So to wrap up our use case section here, our takeaways: microservices can bring agility, but they certainly also bring complexity. The second is do what's right for your business and organization. We saw in the mobile pay that they started from the business value and worked out, and that seems to be a pattern that is pretty effective rather than just going blindly for microservices. And then the last one, Cassandra has been a choice for users that are looking to match that scale and availability of their applications at the data tier. So I mentioned tooling a lot throughout that, and one piece that we are not shy about, and we're certainly aware of, is that Cassandra isn't the easiest piece of technology to run. It is difficult. People have run into a lot of problems with it. So some of what we're trying to do to improve that situation is building a Kubernetes operator for Cassandra.
And that's exciting because it gets Cassandra and Kubernetes talking together in the right way. Chris, you and I both are working on that project, and it's exciting to see what people are doing with it. And this is a pretty new thing. Cassandra and Kubernetes have been working in parallel for a long time, and now they're starting to come together. And it's mostly because of how Kubernetes has taken over a lot of the application space. And as we're working on Kubernetes for data, which is a really interesting thing now, because it's like, has not been talked about a lot. And Cassandra Operator is one part of that. And I think we can walk through like how it works and get you familiar with some of the terminology in Cassandra as well. So let's go to the next slide. So just a quick vocabulary primer. If you know anything about Cassandra, this is where you can go get a drink. But if you know nothing about Cassandra, this is some of the terminology that we're going to use when we talk about the operator. So a cluster is the entire database, and it can span multiple data centers. And that's pretty typical, actually. We do recommend that you span multiple data centers for that availability. You have a 0% chance of 100% uptime if you're in one data center. I've ran a lot of infrastructure on Amazon, and I've never been disappointed about how disappointed I would be with running Amazon in one region. Because eventually an AZ or a region will go down because it's infrastructure. So a cluster, meaning one complete data space, should span multiple data centers. Furthering that availability game is the racks. We have rack awareness as well. So data center awareness, rack awareness. And then the individuals inside, the individual components, compute components, will be really familiar. We call those nodes. And so each node is a shared nothing architecture that contributes to the overall cluster's data space, but is only responsible for a certain range of data. So there you go. Now you know everything about Cassandra. Next slide. It'll be on the test later, right, Chris? Yeah. You don't want to do the test.
I hope not.
Well, the test will be easy. Spell Cassandra. So one of the tricks that we're trying to accomplish here is translating the way Cassandra works into Kubernetes world. And not always easy because they are built in completely different paradigms in a lot of ways, but it's still distributed computing. We still have these core concepts of distributed computing where, surprisingly enough, it's distributed, but how it distributes and replicates is really important. We're going to be talking about the CAS operator. This is the one DataStax has put out as open source. There are others. There are a lot of others. But what we're trying to do is translate all of the parts to Cassandra that make it scalable and resilient and bring it into a CRD. And that CRD translates all of the individual, like what you want, your intent. Like for instance, this is where I want to run it. This is how I want to run it. And here's how much I need, the scale aspects. And the operator's job here is to translate what Kubernetes wants to do. So the replication controller, for instance, in Kubernetes has its ideas of when I say I need 3-node cluster, here's my state that I need. So whenever you create your deployment in Kubernetes, you say deploy. And the operator's job is to say, you need 3 nodes, got it. Well, the Cassandra operator is going to do a better job of deploying it, setting up the nodes so they can communicate, and Cassandra will be super happy about the way it's running without fighting Kubernetes in the way that it thinks that it should run. So it's a translation layer. Next slide. And I think, Chris, this is yours.
So a lot of the different things that a human operator would have to do are packed into a lot of the CAS operator code. And what we're showing on this slide are some of the very Cassandra specific aspects of making things run smoothly on a Kubernetes environment. So the first one here is proper token ring initialization, and that's mapping Cassandra's concept of data distribution to the Kubernetes deployment and bootstrapping one node at a time. So this is something that's packed into the smarts of the operator. And it also is doing other things like the seed node management, which is a concept in Cassandra. You're supposed to start your seed nodes before you start the regular nodes. And also all of the server configuration is integrated into the CRD that we'll take a look at in a minute here. And the operator can handle those rolling restarts because the way that Cassandra works is to apply new configuration changes, you have to restart the nodes. And so if you change something in that CRD, the operator will go and take that and do a rolling restart over your cluster that's deployed in Kubernetes. And by default, the way that the CAS operator works is that it is only putting one replica per AZ, which is a best practice in the Cassandra world, in order to ensure that you have maximum availability in the case of a cloud availability zone failure.
And that's one of those critical things that the operator translates, where Kubernetes is like, here's optimal data placement nodes, put the pods over here. Well, the data placement in Cassandra is well known to the cluster. So we need that translation layer so that we don't have all of our data in one hardware node.
Yeah. And one of the really interesting parts about Cassandra and why we believe it fits well to the Kubernetes world is because there's no concept of a primary or secondary node. So all nodes are equal and they can serve reads and writes. And so mapping that architecture to Kubernetes has actually been pretty nice, though there's still certainly some areas that the Cassandra database world and the Kubernetes world can come together for a bit more harmony than what exists today. So now taking a look at what that Cassandra Data Center CRD looks like, you can see on the left-hand side here that this is really the simplest form of this CRD. This is just a one-node Cassandra cluster. You can see we're configuring the storage config, and also on the bottom we have what would otherwise go in the Cassandra configuration files. So all of this is supplied directly in that CRD. And on the other side here, this is a bit more of a complex example where this would be a 9-node Cassandra cluster. We're mapping that to 3 racks. And again, you can see the various aspects of the server version. The size is the number of nodes. Racks is the distribution that you want for those different nodes. And the operator will take that and allocate the nodes accordingly, such that there will be 3 in each one of the racks.
And what those racks are AZs as well. If you notice that these are East 1B, East 1C, East 1D, this is actually being deployed in Amazon Kubernetes service. So we're able to map, in this particular example, the rack concept in Cassandra in Kubernetes translated to Amazon.
Abstraction, abstraction, abstraction.
Turtles all the way down.
One interesting thing I want to call out here is you do see this management API auth portion of this, and that corresponds to something that's actually powering this operator under the hood. So the way that the Cass operator works is it talks directly to this management API for Apache Cassandra, and this is exposing the various operations to the operator, and then it communicates those to the Cassandra cluster over Unix sockets. And another cool piece about this management API, and there's many of them out there authored by almost everybody that's taken a stab at a Kubernetes operator for Cassandra, but this particular management API is secure by default. So there's the concept of a default super user in Cassandra, and this management API is actually removing that and setting things up with a different user, so that's not exposed by default like it would be on a normal Cassandra installation. But the takeaway is that this management API is really the thing that the operator uses to control the individual Cassandra nodes itself.
And you're welcome for not having to speak JMX.
Yes,
yeah.
it's closed over REST.
That's right. Yeah, that's those of you that have been involved in the Cassandra world, you know that JMX, the Java Management Extension, is how we get into those really juicy details of a Cassandra running cluster. And boy, that can be really difficult. So it's actually really cool. You can run sidecar without running Kubernetes, although we would rather you do it in Kubernetes. The sidecar does provide an HTTP REST interface into some of those really important statistics and management aspects, such as running compactions, repairs, and that sort of thing. So community, we are doing a lot of it. And so there's a community effort right now trying to get together on how we build a Cassandra operator for Cassandra, or sorry, Kubernetes operator for Cassandra, and trying to get closer alignment to the project. There are, I think, how many, 12 did we count? 12 different projects out there, maybe more, that have a Cassandra operator. We are thinking about our poor users out there, and like we feel your pain, and we understand that trying to pick one is difficult. So as a project, this is happening on the Apache side, we're trying to come together on like, how can we build this, at least come together on something. So we do these SIGs, we meet every other week. If you're interested, you can go to the Apache Cassandra wiki, and there's a whole bunch of stuff on there about Kubernetes. We would love for you to be involved. Right now we're in the ideation phase. So if you love to make big ideas, then come and join us. Next slide. And we want you to learn. So this is an opportunity for you to understand how this works. So Chris and I can just sit here and talking about it. You'll get all dreamy. You'll want to do it, right? Well, here's your opportunity. You can go do this for free. We're running workshops every week. You can go see those on YouTube, or you can sign up. There's a sign up for the workshops. But more importantly is what we're doing on /dev. And I realized I created that link in the smaller font. It's more important. Our /dev is there. It's not just for developers, it's also operators. But we have some really cool Katacoda scenarios where you can spin up a Cassandra cluster using Kubernetes. All hands-on, all free, very useful, and there's constantly new content getting put on there. This is one of our missions, is to teach people how to do this properly and to help our community be better. Next, please. And finally, if you just want to give Cassandra a try without having to go through a lot of effort, Astra, DataStax Astra is a service that we have that is super easy to use. You click a couple buttons and you have a running tier of Cassandra. You can do queries. You can understand how the data models work. There's a lot of, it's hands-on guided walkthroughs. More importantly is it's a free tier forever. So if you just want to, I have one running all the time. I have a scratch tier of Cassandra whenever I want to play around with something or try a data model. It's yours for life. And there's no expiration. You don't need a credit card to get it. So that's something you should go claim right away. And by the way, DataStax Astra runs completely on Kubernetes. We have a great blog post about it, don't we, Chris?
We do.
Yeah, you helped write that thing. Yeah, we don't just, we don't talk the talk, we walk the walk. So I think that's
All right.
it.
That's it for us. Are there any questions?
All right, guys, thank you very much for a great presentation. We have some time for some questions. Does anyone have anything that they would like to ask?
Oh, the awkward first question. Who's going to answer this question?
Here's one from John Ray Grant. Where can I find the Discord?
The Discord. Yeah, well, we have a Discord for our workshops and for Cassandra. There's also an ASF Slack, but if you click on if you go to the workshop, DataStax workshops, there's a lot of information on there. Part of that is the Discord link. So yeah, we've been pretty vocal about it on Twitter, on Facebook, LinkedIn, about, hey, join this. You know, there's a community of learners happening right now. So that's probably what you're talking about.
Are we able to run node tool repairs and compactions?
Chris, you just talked about that. Would you like to take it?
Yeah, I had to find my mute button. So that is something that the management API is exposing over REST. So yes, you would be able to run those commands and you would just hit the REST API rather than running node tool directly.
Yeah, it's clear Venkata is running Cassandra somewhere. And I appreciate that because it's not completely hands off. There's still some tasks that need to happen. Kubernetes isn't magic Cassandra sauce. It just makes the deployment a lot easier.
Gavin would like to know, Cassandra data storage on Kubernetes. Do you recommend it without external storage on services like Cobite?
Oh, welcome to my hell. Picking storage in Kubernetes for Cassandra. Actually, one of the hot topics around data on Kubernetes is how do you pick storage? So I'll give you the general guidelines for how to do Cassandra storage, and then we'll talk about the options that are available. When we deploy nodes, let's say on bare metal, we want to have storage as close to the running processes as possible. It's just because being a database that is consistent, meaning that it stores data and is durable on disk, and that is an important part of your latency story. So when you're reading and writing data, the speed of your disk, the amount of data that you can, volumes that you can read and write in concurrency is really important. So of course, if you're using like NVMe drives on a local hard disk, that's going to be the fastest experience. When you get into shared architectures, there are plenty that are just fine. EBS, for instance, is one that we use quite a bit in Amazon, or any of the shared storage provisions that you can do in any cloud provider. OpenEBS has local PV, which is pretty cool. But when you look at your storage system, the question you have to ask is, what's the abstraction layer, and what kind of latencies does it put in between the running database and the storage, the actual bits on disk? I'm not familiar too much with Qbyte, but these are the general guidelines. So things like NFS, which is a good example. NFS is just an absolute no. Most SAN systems are an absolute no. And it's only because when you're dealing with highly concurrent workloads, it can get ugly fast. There are ways to do it. And it has to do with channeling and how you get that data to and from your running processes. That's a really long answer. Chris, do you have anything to add?
And we've seen people do that. So you can, but again, as Patrick said, not recommended.
Yeah, and just keep an eye out. We will be helping our community more with storage options. When you're using any kind of stateful set, which is a part of running Cassandra and Kubernetes, and persistent volume claims, what are you claiming?
How can we handle upgrades?
All right, your turn, Chris.
Yeah, I'll have to check on the latest for this in the Cassandra Operator. I know that it may only be patch version upgrades that are supported, but I'll have to double check that to see what the latest is there, because I know that's been a common question for our team as well.
I think that's going to be something that's going to be more important with, so Cassandra 4.0 is in beta right now. That will be a major upgrade for a lot of folks. And from a project standpoint, upgrading from versions all the way back to, I believe, 2.1 should be a single pass. So I think we would want to make sure that you can do that as well. So you got it right. You upgrade the binaries, run an upgrade SS tables, and you're done.
And what are the C requirements for local development using Kubernetes with the class operator?
I do it all the time. It works with both. It works with both Minikube and Kind. Are you asking for like how many gigs of RAM, how many CPU? All of the instructions for this are also on the DataStax Academy GitHub. There's a Kubernetes workshop repo there that has all of the local instructions for running Cassandra with the Cass operator.
Yeah, if you're doing local work, you can get away with a lot less infrastructure than a production system. Gig of RAM, 1 CPU. It doesn't take a whole lot. We understand the difference between development and production. It's probably worth mentioning we have DataStax Desktop as well, Chris, which deploys Cassandra in a local Kubernetes environment. And then Astra, if you're looking for just a quick Cassandra to play around with.
Yeah. And again, if you want to just purely play with the Cass operator, both Minikube and Kind will work for you.
Yeah, I use Kind now. I switched from Minikube. Is that bad? You probably have some Minikube lovers out there going to be like, come back.
Yeah, it's religious wars. Man.
It is bad. Kind is pretty sweet.
So sounds like a follow-up. So are you able to use stable loader for data loading?
SS table loader. I think we have a better answer for that one, Chris. Do you want to take that or do you want me to?
It should work, but there are other options there. If you need to load directly from SS tables, that would be your path. But there is a DataStax bulk loader and also CQLSH copy if you're looking for JSON or CSV loading. Those are a couple options for you, but.
And remember, if
Patrick,
you're going to stick to it. Well, I was going to say if you have more nodes, you're deploying more nodes than the original source cluster for the SS tables, you can just drop the SS tables directly into the data directory and reindex them. That does work. I don't always recommend it, but like in a development environment, that's perfectly fine. What you need to do is run a repair as soon as it comes back online because it has to redistribute the data. But it's one of the beautiful things about Cassandra is every SS table is it's immutable. So there's not a change state that you have to worry about. And you can read them directly into Cassandra without any trouble.
Okay, do we have any other questions at all?
Now that I gave like the worst possible hack, no, I think we're done here.
Well, actually, there's any recommendations on disk type? As we need to end up using one volume at end.
I feel like I answered that question already, but I'll reiterate. Disk type, well, I'm assuming this is like NVMe versus something more traditional like spinning. The fastest disk as possible, because that's going to in AWS. Thank you. GP2 is awesome. If you're going to use it, it's a really, you can provision how many IOPS and throughput you need. It's really great. This is what we use in Astra on our AWS installations. On Google and on Azure, we have different, we have similar setups, but GP2 is pretty good. Do you know of any others, Chris? Just use GP2. Venkata, you'll be happy.
Anyone else? All right, so looks like we don't have any more questions. That being said, I'd like to thank Chris and Patrick for a wonderful presentation and Q&A facilitation. Thank you everyone for joining us today. The webinar and recording and slides will be online later today. We're looking forward to seeing everyone at a future CNCF webinar. Thank you again so much. Have a wonderful day.